Hi, this is Vinita. Our project is titled A Graph-Based Diffusion Generative Model for Brain Disorder Classification Using Neuroimaging. Coming to the abstract, the main goal of this project is to classify the brain disorders such as ADHD using the resting state fMRI brain scan data. In our approach, we represent the brain as a graph where brain regions are nodes and connections between them are edges. We use a diffusion based generative model called GDDPM to generate synthetic brain graphs. And these generated graphs help to solve the problems like limited and imbalanced medical data sets. Finally, we use a graph neural network classifier to improve the classification accuracy and robustness. Next, coming to the introduction, the brain disorders like ADHD and autism affect the connectivity patterns inside the brain. Functional MRI, also called fMRI, helps us to study how the different brain regions interact with each other. Traditional machine learning methods cannot effectively capture the complex brain relationships. So, graph based learning is used because graphs naturally represent the connectivity between the brain regions. In our project, we combine the graph neural networks with diffusion models to generate realistic synthetic brain connectivity graphs and improve the disorder classification performance. Coming to the dataset details, we used the publicly available ADHD 200 dataset. The dataset contains the resting state fMRI scans of 930 subjects, including both ADHD patients and healthy control subjects. We used CC200 at Brain Atlas, which divides the brain into 200 regions of interest, also called ROIs. From the fMRI signals, we created the functional connectivity matrices that show a correlation between the brain regions. These matrices are then converted into the graph structures. Node represents the brain regions, edges represent the connectivity strength between the regions. We also performed the pre-processing steps like motion correction, normalization, filtering, and the graph construction. Coming to the objectives of our project are to analyzing the brain connectivity using fMRI data, to construct the graph based representation of the brain network, to generate the synthetic brain graphs using the GDDPM, to solve the data scarcity and class imbalance problems, to improve the ADHD classification accuracy using the neural networks, and to compare the baseline and augmented model performance.
Architecture diagram. So we start with our ADHD 200 dataset, which is 930 fMRI scans from people with ADHD and healthy controls. The first thing we had to do was clean this data using three pre-processing steps: motion correction, spatial normalization, and temporal filtering, just to make sure every subject's data is clean and comparable to each other. Once that's done, we use the CC200 atlas to split each brain into 200 regions, grab the activity signal from each region over time, and see how correlated every pair of region is. That gives us connectivity matrix per subject, which we then create into a brain graph, 200 nodes, one per region, and the edges tell you how strongly any two regions are communicating. Next step, we take the real brain graphs and train a GraphSage classifier directly on them. GraphSage basically looks at each brain region, pulls in information from its neighboring region, and builds up a rich representation of whole network that it uses to predict ADHD or control. We do this first just to have a baseline to compare against. The next step is the main contribution of our paper, GDDPM, which is a graph diffusion model. It has two stages, a forward process and a reverse process. In the forward process, we take a real brain graph and at each step, we add small amount of Gaussian noise directly to the edge weight of the graph. So the functional connectivity values between brain regions slowly get corrupted and distorted. In the reverse process, a GCN backbone learns to walk that back. Given a noisy graph, it predicts what it looked like one step earlier. It does this conditioned on class labels, so it always knows whether it's working with ADHD brain or a control brain. Once the model is trained, we feed in random noise and let it keep removing noise step by step. After this, the synthetic graph produced by the diffusion model are merged with the original real training graphs to form an augmented graph dataset that is larger and more diverse. This augmented set is then used to retrain the GraphSage classifier, same architecture as the baseline, but now it has access to much richer training distribution. The entire pipeline runs inside a strict five-fold setup where the diffusion model is trained only on the training fold data and the test fold is always kept completely separate, never influencing the generative model at any stage. And then finally, we compare the baseline and augmented model results.
Hi. I'll just brief about the methodology and the results of our or the implementation of a project. We begin with the pre-processing stage using the ADHD 200 resting state fMRI dataset. The raw brain scans are pre-processed using the Corn toolbox. The three main operations are performed: the motion correction to remove the head movement artifacts, the spatial normalization to align all the brain scans to the common MNI templates, and the third is the temporal filtering to remove the unwanted physiological noise. This ensures a clean and consistent neuroimaging data. Next, we construct Next, we construct the brain graphs using the CC200 atlas, which divides the brain into the 200 regions of interest. For each region of interest, we extract the bold signal time series and compute the Pearson correlation between all the regions paired. These are the correlation from a connectivity matrix where the brain region are represented as nodes and their functional connection is represented as edges. After the graph construction, we apply a graph-based denoising diffusion probabilistic model, GDDPM. During the forward diffusion, noise is added gradually to the real brain graphs. In this reverse diffusion process, a graph convolutional network learns to remove this noise and reconstruct realistic brain connectivity graphs. This allows us to generate biological possible synthetic samples. These synthetic samples are then combined with the real graphs to create an augmented training dataset. This helps to address the challenges of limited data, a class of imbalance commonly found in medical datasets. This classification, for classification, we use GraphSage. It aggregates information from neighboring brain regions, captures important connectivity patterns, and performs binary classification between the ADHD and the controlled subjects. To ensure fair evaluation, we use a strict five-fold cross-validation protocol. This diffusion model is trained only on the training folds, while the test fold contains the only unseen real graphs, preventing any data leakage. Our results show that the diffusion-based augmentation proves that the dataset diversity reduces overfitting and enhances the classification performance. Compared to the baseline GraphForce model, we achieved 8.1% improvement in the accuracy and 6.5% improvement in the F1 score. Thank you.
I'm Dinesh T. I'm explaining result and discussion section. We compare baseline and diffusion framework, whereas baseline resulted in 63.2% and diffusion model resulted in 71.3% of accuracy, and even F1 score improved from 62.5% to 69%. We also verified our synthetic samples by MMT score, that is 0.018, that result in how realistic our synthetic samples are. Also, the functional matrices are being created. Coming to conclusion and future scope. In conclusion, diffusion-based framework successfully generated realistic brain connectivity graph and improved ADHD classification. And the result demonstrate the potential diffusion model as an effective augmentation strategy for neuroimaging application. In future, we plan to extend this framework. We plan to extend this framework for autism, Alzheimer, and incorporate multimodal brain imaging data and improve the interpretability through explainable AI techniques.